Assalamualaikum warahmatullahi wabarakatuh, and very good morning to Dr. Ashraf and Dr. Hafiz. Me and my group will present our project which given title Smart Control Hatching Incubator. Next slide. This is our group members, which is Siti Asha, Arina, Nur Atika, and Sarah. Next slide. Okay, I will do the introduction for our project, which is, as we know nowadays, farmers will be likely to hatch eggs in a large number in a short time. It becomes a problem when the humidity and the temperature are not suitable for the eggs, as when the temperature is too high, the embryos will be dead because of the improper incubation temperature. The smart hatching egg system regulates the temperature during the hatching process. The temperature sensor in the egg incubator system can detect the state of the incubator and automatically adjust the temperature to the best condition for the egg. For our problem statement, for the first one, the egg cannot be hatched because the embryos are malformed due to a lack of temperature management. For the second one, we need higher level supervision for the incubator in terms of temperature. Our objective is included two kind of objective, which is to manage the temperature level of the incubator, and the second one, to design an incubator for the supervision of temperature level. Now I will continue with the hardware part. Next slide. First, I will explain about buffer and latches. In X386, the multiplex pin included 20-bit address bus A19 till A0, a 16-bit data bus D15 till D0, and a 3-line control bus MIO read and write. This is because we need to multiplex these pins to ensure the address of memory and I/O that are required remain valid and stable throughout a read or write cycle. Next slide. For the clock generator, the clock generator used in this project is X4A clock generator, and the purpose of this clock is to generate the clock in an X86-based system. Clock generator provide clock generation, reset synchronization, ready synchronization, TTL level peripheral clock. It also provides clock frequency which is 5 MHz. Thank you.
So I'm going to explain on the memory interface. First, we're going to take a look on the bank selection. The bank selection we use in our project is separate decoder for each bank. This is to save the power. So basically, there are two pins involved in the bank selection, which are BHE and BLE. Both pins are active low, means that it's only activate when we give logic 0. For example, we can take a look on the table for the 0, 0 connection. It will activate both banks. This means we can access 16 bit of data. So if we only want to access high bank, so we only give logic 0 to BHE and logic 1 to BLE, because we don't want to activate the BLE, which is the low bank. So next, to activate the low bank, we give the active 0 to low bank and active 1 to high bank. This is to activate only the low bank. So if we give both pin logic 1, that means we don't want to activate both banks, or neither low bank or high bank will be activated. So for the address determination, first for EEPROM, the minimum address was obtained from the coding, as the static address for the coding is 00000 hexadecimal. So next, for the memory size, we choose 16 kilobyte as we think it will be sufficient for our system. For the maximum address, we calculate the maximum address using the formula maximum address equal to minimum address plus memory size minus 1, and we will get 3 FFF hexadecimal. So for 16 kilobyte size of memory, it consists of 40 lines. So the line from A1 until A14 of the 8086 will be connected to the line A0 until A13 of the memory, which is our EEPROM. So the 8086 consists of 20 lines, which is A0 until A19. So there are lines that are not connected to the EEPROM. So this remaining line will be decoded. So why we need to decode those lines is because we want to correct the address line mismatch between the 8086 and the memory. Next, for the SRAM. So for the minimum address, we need to make sure that the address for the SRAM are not redundant with the address of EEPROM. So we choose the minimum address for our SRAM as 4000 hexadecimal, which is bigger than the maximum address for EEPROM. So the memory size for SRAM that we choose is 8 kilobyte, because we think that will be sufficient for our system or our project. So same with the EEPROM, the maximum address will be calculated using the same formula, and we get 5 5FFFH hexadecimal. So for the 8 kilobyte, it consists of 30 lines. So for the line A0 until A12 of SRAM will be connected to the line A1 until A13 of 80X6. So now I'm going to explain about the EEPROM connection to the 80X6. First, the decoder that we use is 74LS138. So because EEPROM we only involve the read only operation, so only the RD pin will be connected to the EEPROM. So because we choose the bank selection as the bank selection that we choose is a separate decoder for each bank. So for pin A0, it will be connected to the lower bank, and pin BHE will be connected to the high bank. So as you can see in their circuit, there are some parts that I circled. So in those circles, it involved the unconnected line from the 80X6. So those we can call that as the decoding circuit. So not to forget that the MIO pin also be connected to the decoder. Now I'm going to explain about the SRM connection to the 80X6. Same as the EEPROM, the decoder used here is also 74LS138. So SRM can do the read and write operation. So we connect the RD and WR pins to the EEPROM. So the same with the EEPROM. Here we use the bank selection is a separate decoder. So pin A0 will be connected to the lower bank, and pin BHE will be connected to the high bank. Also, not to forget, the MIO pin from the 80X6 will be connected to the decoder. I think next slide. So here is the table for the range of minimum and maximum memory address of EEPROM and SRM.
Assalamualaikum to Dr. Hafiz and Dr. Ashraf. My name is Nur Atika, and now I will give explanation for our hardware I/O part. Next slide. Our I/O system consists of programmable peripheral interface 8255, analog to digital converter, 3 to 8 decoder, 1 input and 2 output. Next slide. In this project, the temperature sensor that functions as the input is used to detect the temperature in the hatching egg system. In order to keep the egg hatched safely within the correct range of temperature, the sensor is an important device in this design. For our output, the LED in the circuit will function as a light bulb, where it will turn on to keep the system temperature remain warm. We use a ventilator in this design to keep the system at or above 38.3 degrees Celsius. If the temperature rises above 38.3 degrees Celsius, embryo will begin to develop improperly. Next slide. We also include analog to digital converter in our circuit design. Based on the circuit, the temperature sensor will be connected to the ADC. Then the ADC will convert the analog signal received from the temperature sensor and then convert it into a digital signal for the PPI 8255. Decoder used to correct the address line mismatch between the microprocessor and memory. We use a 3 to 8 decoder to decode address connection for 8-bit I/O port address A7 until A0. Next slide. 8255 programmable peripheral interface is a popular low-cost interface component found in many applications. 8255 is a fairly simple device to interface to the microprocessor and program. Based on our circuit design, port A, PA7 until PA0 for the PPI is used to connect with our input device, temperature sensor, while port B, PB5 until PB0 is used to connect with the output LED and stepper motor. There is no connection to both the upper half and lower half for port C. Next slide. Our control word 90H obtained from the input and output connection to PPI, and port address DH8, D8H, and DAH is obtained from pin address A7 to A0. We only use D8H and DAH in our coding since only port A and port B are connected to input and output. For the sensor part in the coding, since port A is connected to the temperature sensor, has 0D8H as address and was stored in DX. The memory address of 0DAH was stored into DX, as it is connected to port B, where the ventilator and LED are connected as output.
Okay, now I will present about the flowchart for this software interfacing. Okay, for this flowchart, when we start our system, our temperature sensor will initialize the surrounding temperature of the incubator. And when the temperature is above 37.5 Celsius and below 38.3 Celsius, the bulb to heat up the incubator light off and the ventilator will be closed because the temperature is suitable for the egg. And if the temperature is lower than 37.5 Celsius, the bulb to heat the incubator will be light on, the ventilator will be closed. But if the temperature is high, which is more than 38.3 Celsius, the ventilator will open and it will light off the bulb and it will end the system.
Alright, I'll be continuing the presentation with the coding. The following is the program that we have created based on the flowchart. First, we have made a subpart which is called the sensor. The function of this program is to program how to enter data from the sensor will be inputted. After the data has been inputted, the operation will move to the temperature optimum. Next, at temperature optimum, the value of the sensor will be compared to the value of the range. See, if it happens to be 1, which is the temperature optimum, it will it will perform the action of temperature optimum. However, if it doesn't, it will jump to temperature below. At temperature below, we have indicated 37.5 and below is 0. If the value of the sensor happens to be 0, it will perform the action of temperature below. And if it doesn't, it will jump to temperature above. At temperature above 38.3 is indicated with 2. If the value of the sensor is 2, it will perform the temperature above action. And if it doesn't, it will go back to the temperature optimum to compare back the value. Next. This is the ventilator coding. So in this coding, we have chosen half stepper motor. Since half steps has 11.25 degree and requires 4 steps to change direction. Hence, we need 2 steps to achieve 90 degree clockwise. Why we choose 90 degree clockwise is because we want the ventilator to open and close at 90 degree. Hence, the steps that is the reason why we choose steps direction as 2 heads. Next. At this part, the flow of the program is that for temperature optimum and below, the ventilator will stay closed. For temperature above, the ventilator will turn clockwise, which means the ventilator will open. And after that, after the temperature has decreased to its temperature optimum, which is why we have put decreased AL, the ventilator will close back. It will turn counterclockwise and close back to its initial position. Next. This is the LED coding. For LED coding, we have said that if it's off, it will turn red. If it's on, it will turn green. So in this program, as you can see, if the temperature is below reference, the bulb will switch on. The temperature will then be increased to optimum and bulb will be switched off. In this case, if it happens to be optimum or above, the LED will remain off, which is red. Next. This is the idea on how the result will go out. As you can see, first at below 37.5 degree, it will turn the bulb will light up. However, the ventilator will stay closed. After temperature is increased, the bulb will then turn off and ventilator still stay closed. If optimum, nothing will happen. At case of above 38.3 degree, the things that will change is the ventilator. It will open and after temperature is decreased, it will close back. Next. So in conclusion, the objectives have been achieved well, which is designing the system for smart hatching of temperature supervision and managing the temperature level. This project can help to increase the productivity level of farmers in producing more eggs and chickens, since maintaining optimal temperature is very crucial during hatching. That's all from us. Thank you.